Hello, science students. Our next task is to learn about how to balance chemical reactions. So this is our introduction to balancing chemical reactions video. Your goal is to be able to balance simple chemical reactions. Now, it may seem like an unimportant thing where it's like, oh, I kind of know what goes in, I know what comes out, why do I need to balance it? Well, what that does is it allows scientists and engineers to not just predict what the outcomes will be and how much of what products they'll get, but they can also create reactions as well. And they can be efficient. You don't want to use a lot of extra reactant when you don't have to. So it allows scientists and engineers to make good decisions with regards to the reactions in whatever process they're worried about. So a quick definition to remind you guys about: the coefficient in a reaction is the number placed in front of a molecule to signify the number of that molecule involved in a chemical reaction. So in our H2O2 reaction, the 2 in front of the H2O2, if I were to write that out for you, 2H2O2 becomes 2H2O plus oxygen gas. The 2 in front of the H2O2 and the 2 in front of the H2O are coefficients. They're telling us how many of that molecule are involved in the reaction. Let's take a look at a couple of examples. Our first example is a rust reaction. So iron is going to react with oxygen to create iron oxide, Fe2O3. This is a synthesis reaction because more than one reactant is combining to become a single product. So they're synthesizing one product. Let's try to learn how to balance this reaction. We're going to start by doing the same thing we did in the last video, which in this case is just counting up how much iron and how much oxygen we have in both the reactants and the products. So we're going to make a little T-chart and pick out the elements that we do have. I am now actually going to switch to pencil because this is where mistakes can happen. And not necessarily mistakes, but you have to kind of try things until it works. So first thing I want to do is I want to balance out the iron. Okay, so that one's first. It's tempting to try that one first. Let's try it. So there's 2 irons right here. So let's put 2 right here. Okay, now I jumped ahead a little bit. The very first thing I would normally do is count all the atoms. So at first there was 1 iron and 1, 2 oxygens, and there's 1, 2 irons and 1, 2, 3 oxygens. Those are not balanced, which means we're gonna have to do some work, add some coefficients to balance them out. Now, super common misconception or error is people try to change the subscripts. You cannot change the subscripts in a chemical reaction once it is set, because that changes the compounds involved, it changes the reaction. You can't play with those, you can only change the coefficients. You can change the number of the molecules you have, you cannot change the molecules themselves. Okay, so what does this 2 in front of the iron do? Now I have 2 irons, that seems good, right? It's balanced. So now I'm gonna come over here and try to balance the oxygens. I have a little bit of a problem. If I make this a 2, I have 4 oxygens, that's still not balanced. And I can't do a fraction to make this one work either. So since 2 won't work, I'm going to go ahead and try 3. Okay, so that means I have 3 times the 2 oxygen atoms in each oxygen gas molecule. So I now have 6. It's a little bit of a problem because now my oxygens don't match. Okay, my iron still matches, my oxygen does not. So to get a full 6 oxygen over here, we have to put a 2. That changes the oxygen to 6, changes the iron to 4. Okay, no problem, we can fix that. So instead of putting a 2 in front of this iron to make it balance, we may have to put a 4. So if I put a 4 in front of this iron, I erase and replace the 2. I now have 4 irons, 4 iron atoms, that matches, and I have 6 oxygen atoms. So we have a complete answer there, where we're now balanced. We have the same number of iron atoms and oxygen atoms on both sides of the reaction. So you can see that sometimes this is a little bit of a process where you have to kind of try things out and kind of go around and pick one at a time. Usually you want to pick one of the elements that's by itself to go last. In this case we had 2, which made it a little more challenging. And that way you can balance that one out and then the whole reaction should be finished. Let's look at one more example. This is a combustion reaction of ethane, C2H6, with oxygen gas to become carbon dioxide and water. Let's go ahead and do our starting count. Just like the last one, we'll make our little T-chart. We've got carbon, hydrogen, and oxygen this time. So I'm going to put those on both sides. I have 1, 2 carbons in the ethane. I have 1, 2, 3, 4, 5, 6 hydrogens. There's no coefficients yet. There's 2 oxygens in the O2. I have 1 carbon here. So we're not balanced. That means I'm going to have to do some work. Occasionally they are already balanced. This one's not going to be. Hydrogen, we have 1, 2. And with oxygen, a little bit tricky. There's 2 in the carbon dioxide and 1 in the water. So whenever we change either of those, we're going to have to change the count for oxygen. But for now, we have 3. So all 3 of them not balanced. And this is one where it's important that we kind of keep track of what we're doing to make sure that it works out the way it's supposed to. So first, I like to look at the overall reaction and say, well, the oxygen is the only one by itself. Probably going to leave that one for last. The carbon is not balanced. Let's go ahead and balance that one. If I do that, if I put a 2 here, that's going to make it a little bit better. So now I have 2 carbons, and I have 4 oxygens plus 1 over here still, so I have 5. So I just added an extra 2 oxygens. Those are still not balanced, but we're going to worry about those last. The hydrogen, a little more complicated, right? So there's 6 here, there's 2 here. That means I better put a 3. 3 times 2 is going to give me 6. 3 times the oxygen gives me 3 oxygen plus the 4 over here. Now I have 7. And now we've run into the same problem as the previous question, which is that I cannot make an odd number of oxygens using O2. It's a little bit of a problem. So now here's where we're going to do one of my tricks. So if we double everything, we're going to ignore the oxygen for now. The carbons and the hydrogens are balanced. If we double everything, everything should stay balanced except for the oxygen, and then everything will be an even number. And it looks like we are going to have an odd number of oxygens over here, which means if we double it, it'll become even, and we should be able to use the oxygen gas to balance this out. So let's double everything. So we're going to double the ethane. Now I have 4 carbons here. I have 12 hydrogens. We're going to skip past the oxygen for now and balance that last. We're going to change this 2 to a 4. I'm going to go ahead and erase. So now I have 4 carbons, and we said we're going to double this one as well. It's a little easier to count up everything if we double everything first. So I have 4 carbons. 4 times 2, let's go ahead and do the hydrogens first. 6 times 2 gives us 12. So that's good. These are still balanced, just like I said. 4 times 2 is 8 oxygens plus 6 more gives us a total of 14. So those doubled as well. Now, in order for this to finally be balanced, which is important, is how many oxygens do we need here? Well, we have 2 right now, and we want 14. So we're going to have to go ahead and put a 7 right there. Now, another little hint. Occasionally, what you'll run into is all of these are even. If all of your coefficients are even, you could divide them by 2, reducing it to its simplest form. In this case, we have 3 even ones and an odd coefficient. Therefore, we cannot reduce this. It's stuck the way it is. So this is our balanced reaction. You can always go back and double check these things. So I have 4 carbons, 4 carbons. I have 12 hydrogens. 6 times 2 is 12 hydrogens. And if we look at the 14 oxygens on this side, we have 8 plus another 6 gives us 14 over here. So we are officially balanced. And again, this means to a scientist or an engineer that for every 2 hydrogens, or sorry, for every 2 ethanes I put in a reaction, I'm going to need 7 oxygens to react with it. So the bigger and bigger these molecules get, the more and more complicated these reactions are, and the more oxygen you would actually consume. Okay, thank you guys for listening. I would like to give you one little heads up. These 2 are actually kind of challenging ones. When you do your practice ones, they may not be quite as bad, so don't expect to necessarily do this much work. I just wanted to show you a couple examples that were a little more challenging, so when you go and try them on your own, you're not too intimidated by these, okay? And I just want to make sure we clarify that there are now 14 of those. So thank you for watching, and please give the practice a try. And we're going to get a little more practice with the next video and the next bit of work for you. Okay, thanks for watching.